Alright guys, welcome back. We're going to be solving another question from the second chapter of the Mechanics of Materials by Johnston. We have question 52. And in this one, we have a rod consisting of two cylindrical portions, A, B, and BC, that are restrained at both ends. We know the portion AB is made of steel. We have the elastic modulus of 29 times 10 to the 6 psi. And we have coefficient of the thermal expansion for steel, and also we have the same information for portion BC, and we know that the rod is initially unstressed. We need to determine the normal stress induced in portion AB and BC by a temperature rise of 70 Fahrenheit, and the B part the corresponding deflection of point P. So what's happening in here is that we're going to increase the temperature by 70 degrees, and what's going to happen, these two trying to expand, but obviously the two ends are blocked, so there will be a restriction on the two ends, A and C. So that's going to make another force inside of these two portions. So at the end of this, we're dealing with two different forces in here. One, or actually I should say two different deflections. One of them would be the elongation that is coming from the temperature increase, and the other one would be the compression force that is applying from the wall to each of these two portions. So let's just figure out the elongation because of the temperature. So I'm just going to show it with delta AB, and I'm just going to put a T in here that it's coming from the temperature rise that we have, and the formula that we have is alpha times delta T, or the temperature increase times the length AB, and that's going to be same story for BC as well. Just have to consider different length and also different thermal coefficient. So AB, I believe it was steel, yeah, and the BC is aluminum. So I'm just going to show it with A. Delta T is the same, and we have also different length for each of them. So we'll start with the first one. If we look at the alpha, we have 6.5 times 10 to the minus 6 Fahrenheit. So we're going to multiply this by 70, and also the length is 24 inches. And that's going to give us the elongation for AB. So let's just calculate this really quick. 6.5, 70, 24 times 10 to the minus 6. I'm just going to show it at 10.92 times 10 to the minus 3. So as I said, very similar story for the other one, 13.3, 70, and the length is this time 32. So let's see what we're getting here. 30 times 70 times 32. Oh, sorry. 13.3 times 70 times 32. This is going to be 29.792 10 to the minus 3 inches. So what we know in here is that at the end, the thermal expansion of the whole thing plus the contraction that we have in here because of the force, we can call it P, the force that is forming in these two portions has to be 0, because at the end of the day, the two ends of this rod are restricted. So this has to be 0, or in other words, the delta of the T has to be negative delta of P, and since this is a compression, this will be a negative value. All right, so now let's see what we have in each of them because of the compression that we have that is forming on the two ends. So obviously we're gonna have a force P that is applying on two ends of this, and for AB we need to do a section along AB to find the force in this section, if we look at it, we'll figure out that the other force is also P because of the equilibrium condition that we have in here, and we're gonna have PL times AE for the deformation because of a force. We talked about this over and over in the previous videos. Feel free to check those videos if you need a quick refreshment for your mind. Okay, so this is gonna be P times L. We're doing it for A24. The area, if you look at the figure, we see that we have all the diameters for each of them. So pi divided by 4, diameters 2¼ so 2 times 4 plus 1 9 divided by 4 squared. That's going to be the area, and the elastic modulus also 29 times 10 to the 6. And we're going to have the same story for the other one, PLAE. Again, this was S, this is aluminum, AB. These are BC, and the force is the same. So if you want to find the force in the other or in the portion BC, we can do a cut like this. This is B, the force on the support. So we have to have the same P in here just to satisfy our equilibrium condition. And this is going to be P times the length, which was 32. Pi divided by 4. The diameter is 1½ so 3½ and the elastic modulus of the part BC is 10.4 times 10 to the 6. So our delta P would be the sum of these two, and obviously each of these are negative because they are, if you look at each of them, you can see that they are compacting, so each of them are negative. So basically we're gonna have negative, we can factor P each of these. So if we just call this A, this one B is basically A plus B. So let's just calculate this very quick. So we have two ratios, 1/24 over pi divided by 4 times 9 divided by 4 squared times 29 times 10 to the 6. So it's going to be minus P times basically 208.14 10 to the minus 9 plus the other one is very similar. So 32, this time 3 divided by 2, and this is 10.4. So 741 point, sorry, 1741.18 10 to the minus 9. And this is going to be our delta P, which is going to be a negative value. So 1741.18 plus 208.14, 1949.32 times 10 to the minus 9. And this will be equal to what we explained here. Our delta T, which is the sum of these two values, so it will be equal to 29.792 plus 1092, so 4712 times 10 to the minus 3. And here we can just multiply everything by negative, so delta P is equal minus delta T, and we need to put a negative sign in here. That's how we get rid of the negative signs, and the P will be 40.712 divided by 1949.32. So that's going to be this value times 10 to the 6, or we can just write it down as 2.885 times 10 to the 3, and the unit here would be pounds. And the reason is that our elastic modulus is PSI, so pound per inch squared. So each of the forces that we are getting in here is going to be in pounds. So now that we have the force, the rest of this is pretty easy. We just have to find the normal stress in AB and BC, which is pretty easy. So the normal stress in AB, first of all, is in compression, so it will be negative. The force divided by the area, pi divided by 4. I think AB, the diameter was 5 quarter, sorry, 9 quarters, so 9, and delta BC would be again negative, same force, pi divided by 4, 3/2, and this is gonna give us the stress in each of them, which is the answer for the A part. So basically 2.885 times 10 to the 3 over pi divided by 4 times 9 over 4 squared. So 5,025, 2.66 pound per inch squared, or PSI, or we can divide by 1,000, so 525 KSI, and the other one, we just have 3 divided by 2 in here, or 1.5. It's going to be 11.818 KSI. And both of them are negative, as I mentioned. It's going to be negative value for both. So that's the answer for the A part. And in the B part, we're basically looking for the deflection of point B. So let's just clean up the figure. So we're interested how much this point B is moving. And for doing that, we can either consider the right side or the portion BC, or we can stick to the portion AB. So for finding the deflection of point B, we basically need to figure out the elongation or whatever deflection the portion AB has, which we figured we're going to have a thermal expansion, which was positive, and also we have a compression or shortening of that member because of the force P. So basically we have to find each of these values, which we already know. So it's 10.92 times 10 to the minus 3, the thermal expansion of AB. And for the B part, basically it's the value that we have in here. And now that we have the P, it's easy enough to figure that one out. So basically it's this ratio. First of all, the value is negative. The force was 20.889 times 10 to the minus 3. And what we have in the denominator, pi divided by 4 times 9 divided by 4 squared times 29, 10 to the 6. I missed 24 in here, and this is positive. I don't know why I put a negative. So that's the value that we have for the compression of the AB because of the force on the two ends. So this is gonna give us 4.347, and this is gonna be 10 to the minus 3. So the overall deflection of B would be 1092 minus 4.347, and as we can see, we are getting a positive value, so 6.573 times 10 to the minus 3, which means we had a little bit of expansion because of the temperature, and after that we had a little bit of compression because of the force P, and at the end this will be the new location of B, and that's going to be 6.5 7 times 10 to the minus 3 inches away from the previous point that we had for B. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.